Hello everyone. Today we are going to learn steps to design or fabricate an integrated circuit. And before starting our lecture or to understand this VLSI design cycles in better way, let me show you few slides which is related to the milestone that our semiconductor industry has achieved so far. Okay. So these are the milestone. Back in 1947, the first transistor was invented by these three scientists. Then 1952, first transistor based radio. 1958, first IC. 1965, the famous Moore's law. 1968, Intel. It was founded by Moore and Noyes. 1978, Intel introduced first DRAM. Then this is the picture of vacuum tube. These are the three scientists who invented the transistor. The first transistor was looking like this. Okay, this is the first IC, and this is the first IC by Kilby, first IC by Noyes. Then 1971, Intel microprocessor. 1976 to 81, Apple and IBM came with their PC. Then Xilinx invented the first FPGA in 1984. Then 1985, the Intel, they started focusing on their microprocessor products. Then 1987, the famous fabrication lab TSMC was founded. Then 1991, ARM introduced its RISC IP core. Then 1996, Samsung introduced DRAM. Then 98, microprocessor by IBM. Then 1999 around, SoC came. Then 2002 around, the SIP technology came. Okay. Then after that also we have achieved many more things. Okay. So let me show you one picture, that is SoC architecture. If you want to know more about SoC, then you can check my tutorial, that is IP design. Okay, and it is available. There is a playlist related to this IP. Okay, so this SoC includes memory, then CPU, DSP, communication part. This communication means not like this kind of interfacing. Interface is different. Okay, this is communication IC. You can say this signal communication, then RF part, then mixed signal, JTAG. So it includes everything, analog, then RF, then software part. Okay, so it includes everything, the SoC. And let me show you this wafer to chip. The first one is silicon ingot, from where this IC is fabricated. Then this is die, this is called die. Okay, silicon die. Then most probably this is lithography process. Then at the end we have our IC. This is the traditional VLSI design cycles. Okay, see all these slides I have collected from the internet. I don't remember their name. Maybe I think it belongs to, means these materials, few materials belongs to, I think, NTU, Nanyang Technical University, I think. I'm not sure. Okay, so this is traditional VLSI design cycles. I will explain one by one. Okay, then this is the VLSI design cycle that today we are going to learn. Okay, VLSI design flow. The first one is design specification. And what is this design specification is? Design specification is nothing but a document, okay, a written document or a written statement which contains the functionality, then timing information, then related to area, then power, then testing part, then fault, then coverage. Actually this design specification, there is a separate video that I have uploaded and it is available in my channel. See, I have uploaded videos, I think total 3 number of videos related to front end design. Okay, in that front end design there is a tutorial called specification. Okay, there I have explained, means that video is all about the specification. You can go and check that one. Okay, so I'm not going to explain in details this one, because else it is going to take time. Okay, but still I will show you few slides from that video. So this is a specification part and architecture. I'll not explain all these things. If you want to learn, then you can go and check. Okay, so these are few slides that I have explained. I have already explained all these things. So this is how this device specification looks like. Okay, see, the information that they have given is name of the product, performance, classification, physical characteristic, environmental limitation. So this is a written document, right? This document is called your specification. Okay, see, for example, so this is my key specs. You remember this one? This is, if you want to buy a mobile phone, so this is the specification they mention. So this is called the specification part. Okay, this is what the client gives to supplier. Like, they want this is my specification, and you have to design the IC as per all this data. Okay, then next one is design partition. And what is this design partition is, design partition to form an architecture depending on the functionality, and makes sure the reuse of the design. So again, this is all related to this video, this specification video. Okay, see here, this slide is all about specification and architecture. Okay, so if you want to learn more about this architecture part, then again I will suggest you, please go and check this front end design part, where there is a video called specification. Okay, then the next step is design entity. Okay, so after you got the document, like all the specification, then see, it is like you want to build a home. Okay, you cannot simply build a home, right? First, what we do, we make an architecture, right? Then that means we make a plan. Then we want, suppose I want my kitchen to be here, I want my bathroom to be here, I want my drawing room to be here. So this is what we call the design partition. And specification means how many gates I need, what is the thickness of the wall, how it should look like, what is the color of this building. Okay, so inside, whether we are going to use this what should be the floor. So this is all about design specification and design partition. Okay, and what is the design entity? Design entities is nothing but, once these two things are finalized, then what we do, the next step is to write the code, that is called RTL coding. So design entity is nothing but RTL coding. Okay, then what is this formal verification? Next step is formal verification. Formal verification is test bench. Formal verification, what we do here, we make a test plan. Sorry, we develop a test plan, then we write the test bench. And why to write the test bench? To check whether the circuit and the RTL are same or not, or to verify the design functionality. Okay, so for this functional verification is all about writing the test bench and checking the design, checking whether whatever is specified here, the design specification, okay, and the RTL code that we wrote, whether both are same or not. Okay, So whether we are checking whether the circuit and the RTL are same or not. And here two things come. Okay, first one is the Verilog and system Verilog. System Verilog, what we do, system Verilog we use to write the test bench, and even Verilog is also used to write the test bench. Okay, next point is design integration and verification. And what is the design integration and verification? This one is we integrate all the blocks. Like you, let's say you want to design an adder. So what to do, we design our, let's say we want to design this full adder with the help of two half adder. Okay, so we design this part, this two half adder. Then what we do, we integrate this one. Okay, so integrate all the blocks and test individual component. Okay, so you are testing all the components, means all the blocks, all the small blocks, and we integrate it. That part is called design integration and verification. Okay, next one is pre-synthesis sign off. Pre-synthesis sign off means sign off when all the functional errors are eliminated. So we wrote the code, then we did functional verification using this system Verilog and Verilog. Then we integrate all the blocks. See, first what we do, you make all the small blocks here. Okay, you make all the small blocks, small design. Then you verify one by one. You verify this one, then it is okay. You verify this one, it is okay. You verify this one, it is okay. Then what we do, we integrate all. We integrate all the blocks, all the small blocks. It is like you want to make a register. Okay, register. So your register contains 3 number of flip flop. First flip flop, second flip flop, 3 flip flop. Okay, so what do you do, first you write code for this one, then you write test bench for this one, this flip flop, and you verify it is okay. Now for second you do the same thing, it is verified. You do the same thing, you verify. Then what we do, then we integrate all the blocks. Okay, then again we verify this one, and if it is okay, if there is no error, to check that one whether there is an error or not, that is called design integration and verification. And if there is no error, if everything is okay, then what we do, we stop here. And this part is called pre-synthesis sign off. Okay, next part is post synthesis and design validation. And what is this one? See, another thing here is synthesis and map gate level netlist. Okay, sorry. And after pre-synthesis sign off, what is the next step is synthesis and map gate level netlist. And what is this one? And what we do here, we convert the RTL that we have written, converts RTL to circuit. Okay, and it is done by tools. And what we do here, we optimize is done, and that optimization is related to, so what we do, what kind of optimization is done here, that is timing optimization and area optimization. And why it is done, these steps, the synthesis and map gate level netlist, because if we get better synthesis result, then it reduces the compile time. Okay, so synthesis, if someone asks you what is synthesis, the answer is it is converting the RTL, it is converting RTL to circuit. And what is done here, we do the optimization, timing optimization and area optimization. Okay, then the next step is post synthesis and design validation. And what is this one? This one is check. What we check? Does gate level synthesized logics implement the same input output function as HDL behavior or not? So whatever circuit we got, let's say we wrote code here, okay, code for mux, then it will be converted into the circuit, that logic level circuit. Then it will check input and output. So whatever in see implement same input output function as HDL. It will check whether the input output of this circuit that we got and the HDL we got, whether both are same or not. Okay, this is what is done here, this post synthesis and design validation. So we are validating our design. So whatever code we have written, whatever code we wrote, then that code is converted during this synthesis process, that code is converted into the circuit. So we are checking that one, the circuit that we got and the HDL that we wrote, whether both are same or not. Okay, so this is called your post synthesis and design validation. Then the next step is post synthesis timing verification. And post synthesis timing verification means timing constants like analysis, like critical path. So here the analysis is done. What kind of analysis? Is a critical path. Okay, so this is called post synthesis timing verification. We analyze the critical path and we try to reduce it. Okay, the critical path is reduced if it is more than expected. Okay, this critical path. Then see, after this step, this post synthesis timing verification, we have two options. Okay, whether we want to go for ASIC or we want to go for FPGA. Till then it is same. See, FPGA and ASIC are two different things. Okay, till this point it is same whether you want to design a FPGA or whether you want to design a ASIC. But after this point, after this step, they are separate now. If you want to design FPGA, the next step is placement and routing. Okay, and what is this placement and routing? Placement and routing is related to FPGA, right? That means all these blocks are, what do you call this, placed properly. All whatever code we have written, that one converted into the circuit. Then all these blocks, they means FPGA does internally, and that is little bit, what we can say, this secret. But still, placement and routing means what they do, blocks are placed in proper manner, so that routed means it is a kind of signaling. Okay, routed means, okay, the signals should be routed properly. Okay, placement related to your area, this placement is related to area, and this routing is related to signaling in between these blocks. Okay, so this is called placement and routing. And then the next step is post placement and routing verification. And what is all about, this is timing analysis. It is timing analysis here. What it is done here, the timing analysis, and it is all done by the tools. Okay, you don't need to do this one, timing analysis, and it is related to logic and wire delay, logic delay and wire delay. Okay, and the next is bit format. Okay, then programmable bit is generated here. The last step for this FPGA design is the bit format, bit file generation. And what is this bit file generation is, this is it generates the programming file for FPGA. Okay, so it is all about this VLSI design related to your FPGA design, FPGA. Okay, this VLSI design flow. Then let's see this ASIC flow. Till this point it is same, right? Then the next one is ASIC flow. So ASIC, after post synthesis timing verification, ASIC is, okay. So the next step is For ASIC, the next one is DFT, design for testability. And what is the design for testability? It is another different area, okay, this DFT part is. So the design for testability is test vector generation and fault simulation. So what it does here, checking or scanning all the flip-flop by test inputs or external input is applied here. So what exactly this DFT, I'm not going into details. So see, these are all flip-flops, okay. So if I apply 1 here, if I give input 1 here, so it should be 1. If I apply 0 here, it should be 0 after some time. So what they do, so serially they send 1 0 series of 1 and 0, and they expect the same at the output. And if they don't get here the output, that means there is somewhere some kind of error. So it just checks whether the bits are transitioning. So whatever input we give here, that should be reflected at the output. If it doesn't, that means it is stuck, the 1 or 0 is stuck somewhere. Okay, this is what it is all about, DFT, design for testability. Okay, so we are scanning all the flip-flops and we are testing. Okay, we are scanning and we are checking whether transitioning is happening or not. Okay, the next one is verification. Next step is verification after DFT. Okay, and what is this verification is, verification, this verification is called formal verification. Okay, this is not functional. There is a difference between functional and formal verification. Formal verification, it checks whether the RTL equals to net list or not. After DFT, again what they do, see, already we wrote the RTL code, already we generated the net list. After the synthesis process, the net list is generated. So after DFT, again we are checking whether the RTL equals to net list or not. Okay, so this process is called formal verification. Sometimes they ask what is the difference between formal verification and functional verification. Functional verification is we are checking whether RTL equals to your circuit or not. This is called functional verification. And formal verification, we are checking whether RTL equals to net list or not. Okay, the next step is test generation and fault simulation. The same thing. Okay, this one and this one. I think I have not written anything for that one. So this part is this test vector generation and fault simulation is, it is same as, it is a part of DFT, I can say. Okay, because we are doing this we are providing the test vector and we are checking the fault. Okay, then next part is, this is physical design. From here, this part is physical design. So first step is cell placement or scan insertion, or it is routing. Okay, placement. See, this physical design, it includes, let me show you what is this physical design is all about, what it includes actually. See here, this physical design, physical layout design, it includes partitioning, floor planning and placement, routing, layout editing and compaction, then DRC, design rule check, and layout extraction. So this is physical design. So I'm not going to explain all these parts. Okay, if you want to know more, then you can explore all these points. Okay, but this one I will explain. Okay, this DRC and LBC. See, this in physical design, what the, and always remember this physical design is always related to ASIC. Okay, not FPGA. So this is physical design, then this is layout, then after the layout, the physical layout verification. Next step is physical layout verification. Here two things are done, one is DRC and one is LVS. So let me explain a little bit about this DRC and LVS. DRC is called design rule check. Okay, And this DRC is done by actually EDA tool like Caliver. There is a tool called Caliver. I think other tools may be available, but this Caliver can be used for this design rule check. So it determines whether the physical layout of a particular chip layout satisfies. See, they make the layout, okay, they make the layout using some rules. There are some series of parameters, or that is called rules, okay, some rules are there. So as per the rules, layouts are designed. So that part is checked. The DRC, design rule check, is whatever we have designed, that design is as per the rules or not. Okay, here the input is so DRC, what we do here, the input is this layout, whatever layout we have designed, that one is given, and we give the set of rule. Actually, what are these rules actually? Let me show you what can be the rules for this one. Okay, see, these are the rules, this layout design rules. Like minimum active area width should be lambda in lambda, okay, then minimum poly width spacing, then this one minimum metal width, minimum metal spacing, poly contact size. So these are the rules that should be taken care while you are designing your layout. Okay, these rules during the DRC, these rules are checked. Then the next part is LVS. LVS is called layout versus schematic. So once this layout is completed, then we extract the netlist. Then the layout versus schematic, what we do here, we compare whatever netlist is extracted from the layout with the schematic, to ensure that layout is the identical match to the cell schematic. So you have the schematic, then you design the layout, you got the netlist, then we are checking whether the netlist and schematic are same or not. So this physical layout verification is done by DRC and LVS. Okay, next step is design sign off. Design sign off means if everything okay, then you stops there. So design sign off is if everything okay, then you stop here. Okay, the next one is tap out or fabrication. Tap out is also called fabrication. Okay, the next part is called fabrication, and it is also written GDS2. Okay, what is this tap out? This step, there is a bit file. A bit file is generated. So the last step is it generates a file called GDS2. And what is this GDS2? GDS2 means graphic data stream information interchange. It is a binary file. Okay, always remember this is a binary bit. Okay, this is a bit file, and that is called GDS2. So at the end, what we are getting? We are getting a binary file. Okay, we are getting a binary file, and what information it has? It has the layout information. Okay, so let me tell you one thing actually here. What exactly this GDS2? What is the use of this GDS2? See, what they do. See, here we design our layout, right? We design our layout. Then we got this GDS2 file, the bit file. This bit file is actually sent to fabrication lab. Okay, this bit file, this GDS2 file is sent to this fab lab. Let's say TSMC. Then TSMC, what they will do, with the help of this bit file, they will design mask. You know mask? Mask is designed using the process called lithography. Okay, lithography. Okay. So you understood? Lithography process means we are designing here, we are fabricating the real IC here using this GDS2 file, and this GDS2 file is provided to the fabrication lab like TSMC. They design mask out of this bit file, and that mask is used to design the IC using the process called lithography. Okay, and the last step is verification or validation. That means once your circuit is, that means your IC is fabricated, then for the validation, so whatever we designed, that chip was intended for, whether we are getting exactly the same behavior of our specification. Okay, that is the last part, that is your verification, or it is called validation. That means once your chip came out of fab, then we need to verify, right? So everything is working fine as per our requirement. This is called verification or validation. So this is all about this VLSI design cycle, okay, or VLSI design flow. Let me show you few things. So this is how this physical design, this is the circuit, then the physical design looks like this. And see, this physical design cycle is logic partitioning, then floor planning and placement, routing and compaction, okay. Then this is physical design flow, this is partitioning of your logics, then floor planning and placement, this is routing looks like, then this is compaction, then extraction and verification. So IC design consideration. So what are the points while designing IC that is taken care? The first one is the design complexity, then the performance, then time to market, then definitely cost, then like your power requirement, then signal integrity like noise, okay. So, and another thing is this, what are the issues of VLSI circuit? Performance, area, cost and time to market. These are main four, what do you call this, parameter we can say here. Based on this one, we design our IC or we design our circuit. It can be full custom, standard cell, gate array, FPGA, CPLD, SPLD, SSI, okay. So this is all about this VLSI design flow, and I tried to explain all the concepts, may not be in the details, but why I explained this one, because thinking that at least if you will get to know, then at least, and if you are curious, then you can search all these points on the internet and you can learn more. You can increase your knowledge related to all these things that I explained, okay. So thank you so much for watching, and if you really learn something, then you can like this tutorial, and you can, if you want to watch more videos that is related to VLSI design, then you can subscribe, okay. So thank you so much for watching.